Hey, haha. Now we know how to calculate pH, concentration of H, concentration of OH, and stuff like that. Let's move on to things a little bit more advanced. And let's talk about acid, base, and water. Hey, let's go. Now, before we begin, let's take a look at a new variable, a new term. You know how much you guys love new terms, and that is the variable known as Kw. Okay, this is known as the ionic product of water. Okay, so to give you a little brief rundown about what this is all about, it has something to do with equilibrium. Yeah, this is the same K that you saw with Kc, which is of course your equilibrium constant. Wow, when is equilibrium related to acid and base chemistry? Well, you know that certain type of acid and base are equilibrium reaction. Why? Because they don't fully dissociate. What do we call them? We call them weak. That's right. Weak acids, weak base, they have K values because they don't dissociate completely. In fact, at equilibrium, you'll see more reactants than products. There's a reason why they're weak, because they don't generate that much H's or that many H+. But before we get into that, let's talk about Kw. Okay, the W here stands for water. So you're looking at some sort of equilibrium constant that has something to do with water. Okay, when water is in a pure form, it has a very low concentration of ions in them. Okay, water can go through something known as autoionization, which is what you're seeing right here, where water, okay, can dissociate or ionize into H+ and OH-, and the concentration of these two will be equal, okay, will be equal, because it only makes sense that they do. And this reaction right here is actually an endothermic reaction. So you can pretty much bet that if you were to increase the temperature, let's say you're boiling water, right? If you're boiling water, if this water is not at room temperature, but at near boiling point, you can expect the reaction to proceed forward by looking at Le Chatelier principle, which we talked about back a while ago, I guess, maybe not too long ago, because Le Chatelier principle says if the reaction were to be endothermic, where it releases coldness, okay, where it takes in heat, then if you were to increase the surrounding temperature, the reaction will drive towards product. So this reaction at room temperature is said to be at equilibrium. But if you were to increase the temperature, the reaction will drive forward, creating more H's. Hey, if you're creating more H's, does that mean the pH will go down because there's more H's? In fact, that is actually yes. The pH will go down. However, the overall solution is still neutral because, hey, you can't forget about these OH, because every H you make, you're going to make the same amount of OH. Yes, pH will go down. You're going to have a lower pH because H concentration here is higher. However, overall, your water is still neutral. Okay? Don't tell me that your water is acidic just because you boil it. I don't recall drinking boiled water tasted sour. No, it doesn't. Okay, it's still neutral. It's just that the pH will be lower. Okay, all right, enough of that. So let's talk about Kw. How do we find what the Kw is? So if you look at this reaction right here, you can come up with a Kc expression. And Kc, in this case, is equal to H plus H minus, OH minus, divided by H2O. That would be the equilibrium expression for the autoionization of water. If you were to isolate Kc and H2O, you would have Kc times H2O is equal to H plus and OH minus. This right here is called Kw. Okay, so the equation is as follows, that Kw is equal to H plus times OH minus. And of course, at 25 degrees Celsius, so I guess at SATP, the concentration of H plus equals the concentration of OH minus. I mean, they're always going to be equal. It doesn't take 25 degrees Celsius. They're always going to be like that. But most importantly, they will both have this concentration. Okay? Both H plus and OH minus at 25 degrees Celsius will be 1.0 times 10 to the power of negative 7 moles per liter. Which means Kw at room temperature is going to be 1.0 times 10 to the power of negative 14. That's a very important number. Okay, we'll see what happened in certain calculations that we're going to do that involves that number. Wow, pretty nuts. It's like, man, it's just water. There's so much information that you can get out of it. Well, yeah, of course. It's not surprising, right? So let's do an example then. Let's do a problem. Calculate the H plus and OH minus relationship, or their concentration, of an acid with a pH of 1.8. So let's take a look at how that works. Now, we do know how to convert, hopefully, pH into concentration of H. Because if pH is 1.8, that means the concentration of H, okay, is nothing more than 10 to the power of negative 1.8. Okay, so with my cool calculator, that is actually 1.0 times 10 to the power of 8, negative 8. Okay, so it's not very low concentration. You can't expect a pH. That's why, of course, pH is kind of low here. Okay. I think I made a mistake. This doesn't look right, doesn't it? Of course it doesn't. Must have typed in something else. Okay, the answer should be 0.016. Oh my goodness. Yeah, that almost gave me a heart attack there. Okay, all right, we found H plus. Now let's find OH minus. Now remember, the relationship is that Kw is equal to H plus times OH minus. Okay, Kw is a constant. It is 1.0 times 10 to the power of negative 14. H plus we just found to be 0.016. And I'm sure you guys are going to be able to solve for this, right? Okay. Let me just solve this for you. Okay, that OH is going to be kW divided by 0.016. And the answer, of course, is 6.25 times 10 to the power of negative 13. Okay. That's pretty easy. Now, there's other ways of doing it. We actually have done these questions before. It's just that we haven't done it like this. Right? We haven't done it like this. Because you can always do this, if you remember correctly. pH is 1.8, right? Well, what is pOH? Well, I remember that pH plus pOH is equal to 14. If pH is 1.8, pOH must be 12.2, right? So if you take the antilog of pOH, you actually get the same number, believe it or not. I'm sure you believe me, right? So I guess that's something you can check if that sort of interests you, okay? But I'm sure you'll get somewhere close to that number. All right, let's continue. Man, well, that was a bad mistake over here. What was I thinking? At least I catch it before you guys catch it and tell me on the comment section below. So now let's talk about strong acid. Okay, we talked about this before, but let's kind of like reiterate what I said. We'll do So strong acid. What makes a strong acid strong? Well, they fully dissociate in water, or in this case, they fully ionize in water 100% of the time. And the reaction should be like this, with no equilibrium sign. HA represents some sort of acid. It could be a binary acid or an oxy acid, it doesn't matter. But when you put that in water, you're always going to get H plus and A minus, always. And the ratio is 1 to 1. So if you have 5 moles of acid, 5 mole of HA, you're going to get 5 moles of H plus, 5 moles of whatever anion. So let's sort of do this a little graphically right here. So here's a beaker of water, okay? And here's your acid. Because it is a strong acid, it will 100% dissociate. Okay? So as I said, if you have, let's say, 5 of these, once it's in water, it will ionize to give you 5H plus and 5A minus. Okay, that's, I guess, the beauty of this. Now, let's do one step further. Let me just erase this a little bit. Let me just blow this up. H2O. Right there. Okay? You won't have these guys floating around in solutions. You really don't. Okay? These guys can exist in solution as an anion, no problem. But H plus being a cation floating in water, that doesn't happen very often. So what happens in reality is that they get picked up. They form a coordinate covalent bond with water, where water will share both of its electron right here, one of the lone pair electron, towards H. So what you really get here is a secondary reaction, you can say, that H plus actually get together with H2O to give you H3O plus. Okay, and if you look at the ratio, the mole ratio of H plus and H3O plus, they too is going to be 1 to 1. So you can even say the amount of H plus you get is the same concentration as H3O plus that you're going to get. Now, this is going to be very, very important once we start looking at equilibrium, okay, of weak acid, stuff like that. And you just have to know whatever H plus is really the same as what H3O plus is. Okay, well, let's not talk about equilibrium yet because we're looking at strong acid. So what are some examples of strong acid and in terms of what they do? Well, I have 3 examples of strong acids like hydrochloric acid. Okay, hydrochloric acid, when you put that in water, you're going to get H3O plus and you're going to get Cl minus. Okay, here's another strong acid for you, sulfuric acid. You put that in water, or you react that with water, you'll get, again, H3O plus, because you picked up a hydrogen from H2SO4, and what you're left with is HSO4 minus. Okay, and later on we'll actually kind of talk about, will this continue to dissociate to give you another H3O plus SO4 minus. That's called polyprotic, and we will talk about that later, way later. Well, let's do one more. Nitric acid, NO3. Okay, if you were to react this with water, just by immersing it in water, you'll get H3O plus, and of course NO3 minus, nitrate ion. Okay, these are all strong acid. What that means is that they all will have some sort of 100% dissociation when they're in aqueous. Okay, that's, I guess, the beauty or not so beauty of being a strong acid. All right. Let's take a look at weak acid. What makes a strong acid strong is what makes a weak acid weak, and it is the dissociation, the percent dissociation. So as an example, right here, vinegar, acetic acid. Acetic acid has an approximately 40% dissociation. Okay, now let's take a look at what that means. So here's my beaker of water again, and here's my acetic acid, CH3COOH. If I were to drop this in water, I will get H plus and CH3COO minus. Now, unlike last time, where the dissociation is 100%, the dissociation here is only 40%. What does that mean? Well, let's say you have 10 of these. You have 10 of these. You're really only going to get 4 H plus, 4 CH3COO acetate, and you're going to get 6 CH3COOH. So just like what this 40% says, only 40% of this, which in this case is 4 out of 10 of these, are going to break apart. It's almost like you have 10 couples, and the divorce rate is 40%, and only 4 out of the 10 will get into a divorce. whereas the other 6 are still very much in love. That's weak acid. That's what weak acids do. That's what makes them weak, because you're not going to get as much of these compared to these. Because for strong acid, oh man, you put 10 of these in there, you're going to get 10 of these. You're going to get lots of H+. pH is going to be low. For weak acid, pH might be low if this was a very high in concentration, but if not, you're not going to get as much because they don't fully dissociate. Okay? Hence, this equilibrium sign is here. Okay? Meaning that, yeah, you're going to make H+ and A-, but at times this reaction can go back to make HA. In fact, for weak acid, this right here dominates more than these. So the drive here is certainly pointing left. Certainly pointing left. Okay? So that's acetic acid for you. That's acetic acid for you. So that's weak acid in terms of why it is weak. What about strong base? A strong base is also known as an alkaline. To become a strong base, there's a full dissociation, just like strong acid. 100% dissociation, where some sort of metal hydroxide, and what is this metal? Well, Na, K, Ba, Li, these are all strong, okay? They will fully dissociate. Like, for example, NaOH, okay? In water, it will fully dissociate to give you Na plus and OH minus. No, KOH, it will fully dissociate to give you K plus and OH minus. Now this one you have to be careful. Okay, barium hydroxide. You'll get barium 2 plus and OH minus, but not one OH minus, but you actually get 2 OH minus out of this. You can have to balance it, right? So I guess something to keep in mind. Just something to keep in mind. Now, if it's not these guys, all the other bases that you will see are going to be weak bases. That's just the way it is. Okay, but these are obviously are strong base. They make lots of OH. pH is going to be high towards 14, and those are known as alkaline. What about weak base? Now, weak base is a little special because there's 2 types here. There's some hydroxide ones, and there are ones that have no hydroxide, but for some reason they can still produce OH minus, just a little differently. It involves water. So let's take a look at this one in terms of how that works. Now, just like weak acid, the dissociation here is less than 100%. You're not going to get as many OH as a strong base will. So let's take a look at an example. Here's my beaker of water again, okay? And here is a popular base, ammonium hydroxide. People use that as a cold pack, okay? Because this guy has a pretty high delta H when it comes to endothermic. So if you drop this in water, you're going to get, NH4 plus, and you're going to get OH minus. Okay, and it's not going to be 100%. I don't remember what it is. So let's say it's 10%. Okay, let's say this is 10% dissociation. So if you have 10 of these, you're probably just going to get 1 OH, 1 NH4, and then you'll end up with 9 NH4OH intact. Okay, so that's looking into a weak base. But what about this type of weak base? This is a little different. This is known as Bronsted-Lowry base. Yeah, different types of base. We kind of talked about that already, where you have some sort of base reacting with water. And what happened is that this base is acting like what we call a proton acceptor. He's going to accept one of these hydrogen to become BH+, leaving water to just OH because it got one of the H's got taken away. Okay? As you can see, what's the similarities between these two? Well, both has OH as a product. Just different ways of doing it. This is by dissociation. This is by having some sort of proton acceptor taking away one of the hydrogen in water. A popular example here is ammonia. Okay? If you drop ammonia in water, and here's water, okay, what ammonia is going to do is ammonia, right here, let me look at this a little bit bigger. Maybe I should draw it like this. Okay, ammonia will says, hey, water, let me take one of your hydrogen with my lone pair. Okay, you can keep these two electrons as, you know, with oxygen to turn himself into an anion, no problem. So because of that, let's kind of draw this. Let's kind of take this away, and these two electrons will go over to oxygen, and what you'll eventually get right here is ammonium cation and hydroxide. Anion. Okay. A different way of looking at base, but base nonetheless. However, dissociation here, or no, there's really no dissociation here, but well, there is a dissociation here. The dissociation is between water. Okay, the dissociation is water breaking up to be plus H plus and OH minus, where the H plus gets picked up by NH3. Okay, the dissociation here obviously is not full. That's for sure. Okay. Anyway, that's weak base. A little bit more difficult, I guess, than weak acid because of Bronsted-Lowry base, but this is something that I hope you guys understand. Okay, there we go. Okay, Bronsted-Lowry theory. And in this theory, acid is known to be what we call a proton donor. So when you take an acid and you drop it in water, it gives you H plus and Cl minus. As you can see, acid is a proton donating thing. Base, as we saw earlier, is a proton acceptor, like NH3. Okay, upon saying hello to water, it will take one of the hydrogen from water and become NH4 plus. That's a proton acceptor. Because of that, that brings us to something known as the conjugate acid and base. Okay, let's take a look at example 1. This is what happens to a strong acid. Hence, the arrow is unidirectional. Okay, you're going to get a lot of these, whereas you're not going to get any more of those, depending if there's something in excess, of course. Now, in this case, let's see what's happening. What's the fate of each participant? If you take a look at HCl, HCl actually becomes Cl minus. So how did it do that? Well, it lost a hydrogen to do that. It donated a hydrogen to become that. Hey, what did we say here? Proton donor is an acid. So HCl is an acid. Let's call it A. Okay. Let's take a look at his friend, H2O. H2O becomes H3O. How do I do that? Well, I pick up an H to do that. I'm an H picker upper, if there's such thing. Okay? Whoa, isn't that a proton acceptor? I am a proton acceptor. A proton acceptor is a base. So I am actually acting like a base. Okay? Now, let's take a look at the product. Normally, we don't give any of the abbreviation here because it kind of makes no sense to give these guys a title because these guys are not going to go back. But let's just say it does. Let's just say these guys can go back, but it actually doesn't, and I'll tell you why very soon. H3O, if we were to go back, becomes H2O. In order for me to do that, I donate a proton to do that, right? H3O going back to become H2O, I lost an H, I donate an H, and a H donor is called an acid. So H3O theoretically is an acid, but you can't just call him an acid because you already call him an acid. We're going to call him a conjugate acid. Okay? Same with Cl minus. Cl minus becomes HCl. How do I do that? I accepted a proton to do that. Proton acceptor. That's a base. Being on the right side here, going backward, it is a conjugate base. Now, as I said, this and this really isn't, it doesn't mean anything here. It doesn't mean a whole, anything. Because these guys are not going to go back. This guy's not a weak acid. This guy's a strong acid. This guy can only go forward. Why is that? Well, the reason is this. What makes a strong acid strong is that H2O is a much stronger base than Cl minus. These guys are both base, but this guy's a stronger base. This guy says, I pick up H way better than you. I pick up protons more often than you. Because of that, you're not going to have a chance to pick up nothing, man. I will pick up all of these and become H3O. You, being a weaker base, you're not going to pick up these guys and become HCl because I dominate. I dominate you. Okay? So, the reaction is going to be towards product all the time. Because H2O is just a better base than you. Okay? But, what about example 2? The difference here in example 2 is that you're looking at a weak acid here. This is acetic acid. This is your vinegar again. We saw it has a dissociation less than 100. Well, let's give them a title, should we? This guy is an acid because he's going to donate this H. Water is a base because water is going to accept an H. Now this guy is a conjugate acid, this guy's a conjugate base, and it makes perfect sense that they are, and they should have that title, unlike these guys having a fake title. These guys are legit because H3O will become H2O, and guess what? It does it more often than this. Basically, in this reaction, reactants dominate more than products. Why? Simple. Simple. Because acetate is a better, or in this case, stronger base than water. Okay? This dude right here, he's like, I can pick up H better than you pick up H. So the reaction drives this way. All right? So that's just, I guess that's just the way it's supposed to be. And as you can see in this page right here, water, okay, can actually act as an acid or a base depending on who he's dancing with. I can give you another example later on that where water is acting as an acid. That can happen. And because water has that capability, water is said to be amphoteric. Okay? So, let's summarize this. Okay? That strong acid usually has a weak conjugate base. For weak acid, it has a strong conjugate base. Just something to, I guess, keep in mind. All right, let me just finish this off by showing you a base reaction. So let's say I have NH4 NH3 plus water. We've seen this before. This will give you NH4 and OH minus. Okay? Let's blow this up. Here in this case, NH3 is a base because NH3 becomes NH4 by proton accepting, which means H2O becomes OH minus because it proton donated. So this is an acid. If you were to go backward, NH4 becomes NH3 by proton donate. So that's a conjugate acid. And obviously OH becomes H2O. That's a base, and that's a conjugate base. Okay? What makes this weak is that the conjugate acid here is stronger in terms of donating proton than water donating proton. Okay? This one is more willing to say get rid of one of the H than this guy saying get rid of this H. So that's why the reaction probably drive this way. Okay? And just to prove that water is amphoteric, here you can see water is acting as an acid. In these cases, water is acting like a base. Water is special, isn't it? Anyway, that's it for today. Okay, and we're going to be talking about another K value next time. All right, bye now.